Hi everybody, we're moving forward in chapter 16. We should be done with 16, I hope today. We'll get into 17, alright? So we're moving towards the idea of synthetic strategies, we'll say. Synthetic strategies to make benzene derivatives. And we're using all the knowledge from chapter 15 and chapter 16 to eventually synthesize benzene derivatives and use some kind of cool strategies. What we sort of ended on last time was kind of the effect of multiple substituents on a benzene, and how maybe one has a higher priority or a lower priority, and kind of like the interplay of the different substituents, right? So without going into incredible detail, this is all from last lecture. We had a couple guidelines, and maybe the most important one is guideline number 1, which is the activity order. Well, one of the most important guidelines, which is that NH2 and OH were the greatest activators. Like there's like their own little group 1, I guess, I don't know. And then if you have an amide, so NH acetyl bond O, or a ether, OR, it's going to be OCH3 or something, that's a second group, so they have a lower precedence. And then if you have an alkyl group or a halogen, that's the third group. And then everything else is kind of like the lower priority group, strong electron withdrawing groups, and those are like nitro, CF3, ketone, aldehyde, etc. Generally speaking, the strongest activator wins. So if you have a strong activator, it basically makes it gets to decide where the new thing is going to go. If you have the option of ortho, it's usually not favored. And it's usually not favored. So like in this case, chloro is the greatest activator, because this is group 3, this is group 4. They happen to be saying the same thing though, because this is an ortho-para director, that's a meta director, right? So ortho-para to this would be this position or this position. Those happen to be meta to the nitrile, so it's not really a competition effect, but ortho is less favored, right? So that kind of puts whatever the new thing we're attaching would go to this position. Okay, this kind of weird thing was like a ortho, it's a diether. Well, they're both ortho-para directors, and they're both in conflict with each other. So it would go to one position or the other, but those are basically the same position, right? And those are para to one or para to the other, but whatever, we just pick one of them. But the big thing is it's para to it and not ortho to either of them, because para would be more favored. Okay. And then guideline 4 was basically just saying as you add more substituents, these same rules take effect. So not just a couple more examples. And now we're kind of into this section called synthetic strategies toward substituted benzenes. Okay, number 6, synthetic strategies towards substituted benzenes. So we're going to describe a couple strategies, like tricks we can do that simplify the construction of substituted benzene derivatives. All right. So there's a few of them, and just make note of each of these strategies. The first one is that we can kind of use protection. And by protection, we've seen that sort of be a like attachment of a functional group to maybe block something, or maybe prevent reactivity or something like that. But the whole point about protection is you can always deprotect, so you can add something and then remove it. And what we're going to do here is we're going to modulate. So protection modulates activity of a ring. Protection modulates the activity of a ring. Another way, other words I'll use to describe this are temporary deactivation. Okay, because remember, some things are really active, and if they're overly active, it may actually cause problems, and we'll see that. Okay, so what if we have aminobenzene, or it's aminobenzene, it's also called aniline, aniline, A-N-I-L-I-N-E, aniline, and we throw in an electrophile. Okay, and we know that this is an activated ring, right? Is it a highly active ring or a lightly active ring, or we know it's an activator, NH2 is an activator. If you remember the last section, number 5, we talked about like what are the greatest activators. Well, this is an incredible activator. This is in the super active group to the extent that it's actually a problem. NH2 will activate the benzene, and you will likely get 3 electrophiles incorporated. So it's so active that it doesn't want to stop. It's a orthopara director. It's going to attach something in the para position. Then it's probably going to attach some things in the ortho positions too. So that's a problem if you only want to attach one thing. If you do want to only attach one thing to the benzene, where would you usually attach it? Would it be the para position or the ortho positions? Probably go to the para position, because para is usually more favored than ortho. Okay. All right. So how can we do that? Is there some kind of strategy where we can maybe temporarily deactivate the nitrogen so that we can incorporate something like a single electrophile? And the answer is yes. So the trick is to start with the NH2, and we're going to convert it to an amide. Okay, so now we're NH2, now it's a amide. It's a this is called acetamide, A-C-E-T-A-M-I-D-E, acetamide, and yeah, okay, so this is group 1, right? What was this? Remember our little group chart? This is group 1, this is group 2. This is slightly less active, right? So by being slightly less active, we throw in an electrophile, right? Where's it going to go? Where's the electrophile going to go? I'm trying to separate the label acetamide from this arrow. Okay. Where is the electrophile going to go? This is super active, this is a little less active. So it's going to go to the para position, which is exactly what we want. Okay? The one question will be, how do we put this on? I'll tell you that in a second. Alright, so now the only question, if our original goal was to take this and attach a single thing to the para position, this is pretty good, except now we got to get rid of the amide, and we have to hydrolyze off the amide using some stuff that we'll learn about a little bit later in the course also. Okay, so, sorry, here we are. Alright, so what we're doing is we're going to protect this with an amide, do our EAS reaction, EAS, and then we're going to have this product with a single electrophile attached, and then we can wipe away the amide using another reaction. So I just got to tell you what those reactions are. The mechanisms will be a little later in the course. Okay, so the first one is kind of weird because this is also an EAS reaction, chapter 15. This is used in the Friedel-Crafts acylation. But in the Friedel-Crafts acylation, we also add aluminum, right? AlCl3. So we're not adding aluminum. This is not a super electrophile. This is just a normal electrophile. And we also add base, pyridine. Pyridine, which is a benzene with 3 nitrogens. It's a mild base. Okay. So right now I'm just going to say no mechanism. It will be later in the course. I forgot what chapter, 23 or 22 or something like that. So you'll learn about this mechanism a little bit later. It's something about, the nitrogen attacks the carbon and kicks off the chlorine, but it's not a simple like SN2 reaction. There's a little bit more to it. All right, so we'll learn about that mechanism. And to deprotect, it's H3O plus. It's acid, water, and heat, usually. Acid, water, and heat will cleave this amide into the amine. Byproduct is acetic acid, OH. I'm going to put parentheses around it because that's not really that big of a deal what the byproduct is here. But it's basically hydrolyzing the carbon-nitrogen bond. So yeah, and that it hydrolyzes and you get the deprotected thing. And sometimes I use abbreviations. I'll skip the abbreviations for now. All right. So anyway, that's a trick. That's our first strategy. Protection modulates activity of a ring, and we're temporarily deactivating the ring by making an amide, doing our cool reaction, and then we're deprotecting with H3O and heat. Okay. Another example of the same idea. Okay, so NH2 was a group 1 activator, right? And what was the other group 1 activator? NH2 and OH. Remember that? That was also end of last lecture. Well, it does the same thing, and it's overly active, and so you can it'll typically add at least 2 electrophiles, if not 3. So I'll put one of them in parentheses because it's not always going to add 3. It kind of depends on what the electrophile is. Okay, so same kind of problem, right? Same kind of problem where we have an overly active substituent and we get over incorporation of electrophiles. So if you remember, if you remember, this is a group 1 substituent, OH. What was the group 2, the other group 2 substituent? So this was a group 2 substituent. The other group 2, if you go look back, is ether. Okay? And if you make an ether, you throw an electrophile, well, that's less active, and now you get your nice single attachment of an electrophile. Same exact strategy. Okay? Now think back to organic 1. How do you make ethers? That's actually really easy. You do know the reaction, and you do know the mechanism of this. So typically it's going to be a base, like NaH, and then it's going to be something that attaches a methyl group, maybe methyl with a leaving group. So it's methyl with a leaving group. Like, what's your favorite leaving group? Maybe bromine or iodine, like methyl iodide. Why would you use methyl iodide instead of methyl bromide? You may have learned this, but methyl iodide is actually a liquid. Methyl bromide's a gas. It's at really low boiling. So at room temp, methyl bromide's a gas, and we'd rather not use gases. But if you write methyl bromide, whatever, it's fine. So this is Williamson ether synthesis. It's chapter 9 reaction. You might want to review this. It's really easy though. Base NaH, it's like H minus, right? H dot minus. H minus takes proton, puts electrons on oxygen, makes it O minus, and the O minus attacks the carbon in an SN2 reaction. So this is an SN2 reaction. The Williamson ether synthesis is an SN2 reaction to make ethers. Okay. All right. So we attach the electrophile, and now what would we need to do if we had our goal of just attaching a single electrophile to the para position, so what do we need to do now to get rid of that electrophile? And not the electrophile, the CH3. If this was our goal, how do we proceed? What do we need to do? We got to get rid of the ether, right? So this is actually also chapter 9. Anybody remember? Do you guys remember how to cleave an ether? You've probably forgotten everything from Organic 1. But ether cleavage is pretty easy with strong nucleophilic acids. HI is the one to use. I'll actually show the mechanism of that real quick. It's really easy. Oxygen, lone pair, attacks proton, and kicks off iodide. I'm just going to say AR for the aromatic ring. O, H, CH3 plus charge. Okay. Now you got nucleophilic iodide. Nucleophilic iodide, you have a methyl with essentially a leaving group on it, so what's it going to do? Attack. And that gives you what you want. Your product is actually the leaving group, right? It is the leaving group, but it's nevertheless, that's the product. Of course, what's your other material that you make? Methyl iodide, or iodomethane, ICH3. Okay, cool. So yeah, this is another strategy, and the name of the strategy is temporary deactivation. Okay, cool. Alright, so we're still on number 6, which are these synthetic strategies. Next strategy, the name I'm going to give it is, or letters B. The name is going to be modulating, which means kind of changing around, the directing behavior. Modulating the directing behavior of a substituent. Modulating the directing behavior of a substituent. What that basically means is, if something is an ortho-para director, I can do some magic stuff to convert it maybe to a meta director, which is pretty cool. Pretty cool. Alright. What's an example of this? What's an example? Think about nitro. Now nitro is what kind of substituent? Is it ortho-para or meta? Think back, look at your index card or whatever. Nitro, is it ortho-para or meta? And it's a strong electron withdrawing group, and it's a meta director. So I'll go downward and draw electrophile, and I'll say, where is that electrophile going to go if this is a meta director? And the answer is to the meta position. Alright. Wouldn't it be cool if I could somehow turn that into an ortho-para director? And then back to, so turn it into something else and be able to attach stuff either to the ortho or para position or whatever, and then return it back to a nitro. This is a meta director, but can I convert it to an ortho-para director? In order, for the purpose of installing the electrophile like at the para position? Wouldn't that be cool? And the answer is yes, we can. So I'm going to use kind of these sort of reversible arrows to show that I can interconvert this to something else that happens to be an ortho-para director. And what it is an NH2 group. So a nitro is actually kind of an oxidized functional group. If it's an oxidized functional group, you see all the oxygens, I can reduce this to an NH2, which is an ortho-para director. Okay, and so the reducing agent is H2 nickel, I also abbreviate this bracket H bracket, bracket H bracket, which is a abbreviation for reduction. Okay. There are other metals like palladium, like H2 palladium, we'll say, or H2 palladium. There's other ways. There's probably 1,000 ways to do this, but the book kind of emphasizes H2 nickel, so you should know that. And how do I go the other way? If I have an NH2 and I want to return it to the high oxidation state, in order for this to be useful, I need to go back and forth, right? Well, first, what's the abbreviation for oxidation? This is the abbreviation for reduction. The abbreviation for oxidation is bracket O bracket. Okay. What's the reagent? So it looks like trifluoroacetic acid, but it's got an extra oxygen. So it's F3C, C double bond O, OH. It's a weird thing that kind of looks like a carboxylic acid, but it's got the extra oxygen. I'll say MCPBA. Remember MCPBA? What you use to make epoxides, right? This kind of looks like MCPBA in some ways because it's got the extra oxygen. So if you compare this to MCPBA, you'll see that. Alright, so that's the oxidizing agent. No mechanisms for either of these. So don't worry about mechanisms of these reactions. No mechanisms. I know you love mechanisms, and I love mechanisms. I could probably hypothesize a mechanism, but I'm not going to do that. Okay, so we've basically turned a meta director into an orthopara director. But we also learned in the last section, in A, that this has a problem. This is a overly active orthopara director, right? It's overly active. It goes crazy if you throw an electrophile. What happens? It's overly active, so it's going to put it all over the place. It's going to say, well, I'm an orthopara director, and I'm going to put an electrophile at both ortho positions and the para position. Okay. Sometimes you want that, but oftentimes you don't want that. And so what we could do is sort of this little roundabout sequence we just did in the last strategy to essentially protect, attach something, and then deprotect it, right? So we have that option too. We can protect it, attach the E, deprotect it, and then we get to this point. So now we have a couple options, right? And this is cool because now it's opening doors for us to do cool synthesis. For example, what if I want to take nitrobenzene. Actually, I'm just gonna, here, let's just do this. Let's say yeah, I'm gonna go back to what I was gonna try. Nitrobenzene. I want to take nitrobenzene and I want to convert it to nitrochlorobenzene. 4-chloronitrobenzene. Alright. I want to do this. How am I going to do this? Is there a magic way to just attach a chlorine? No, because that's a meta director, right? So we're going to have to do some fun multi-step synthesis, right? Nitrobenzene to para-chloronitrobenzene. We're probably going to have to combine, what we just learned up here, which lets me modulate the directing behavior, and we're going to have to combine with this, which is basically section A, the last one, which allows me to temporarily deactivate the NH2, attach something, and then return it back to NH2. Okay? So what's the first step? And what's the last step? I don't know. We can kind of figure out what the first step is. We can figure out the last step. We can kind of work our way back. First thing is that's a meta director. That's a problem, right? So let's just maybe, I don't know. I'm kind of combining forward synthesis and retrosynthesis. Okay. Probably do a reduction. How do you reduce nitro to NH2? It was H2 nickel. It was right up there, right? And then like this is a case where sometimes, retrosynthesis really helps you. Sometimes you can just kind of go in the forward direction. The last step is probably going to be the opposite, which is NH2Cl to NO2Cl. That's an oxidation. What's the oxidizing agent? Well, we look up here in our little notes. That's the oxidizing agent, the trifluoro C double bond O OOH. So CF3OOH. Cool. Alright, so now it's like we got this, we got to do this. But remember, we can't do this in a single step, even though this is, it looks like we just chlorinate the para position, right? Chlorinate the para position. But we can't do that because of the overactivity. So now we have to basically do protection, chlorinate, deprotection. Okay? Yeah, so we just follow our little cheat sheet, or our notes. First you gotta attach the amide. This is the previous strategy, last page. Acid chloride. No, we're not using aluminum trichloride, we just use a mild base, pyridine. PYR ... is an abbreviation for that. Pyridine, or it's a benzene with a nitrogen in it and a lone pair on the nitrogen. Okay? Alright, then we do what? Now we're ready to chlorinate, and this is not an overly active orthopara director. So chlorine, FeCl3. Sweet. All we got to do now is what? We got to wipe off the amide. How do we do that? We hydrolyze it. H3O plus. Heat. And there we go. We've done it. Alright, cool, that's fun. We have another type of this sort of same strategy, modulating directing behavior of substituents. Let's show the other one now at the bottom. So this other one is, say I have a ketone. Make it fun and add extra carbon. Alright, we have a ketone. Say we throw in an electrophile with this ketone. Where is it going to go? Is it going to go orthopara or meta? Well, is a ketone an orthopara director or a meta director? And it's a meta director, right? Ketones, it's all the C double bond O's, N double bond O, S double bond O, CF3, those are all meta directors. So it's the same kind of situation. And now we have our meta thing. Wouldn't it be cool if we could somehow turn this into a orthopara director? Wouldn't it be cool? And the answer is yes, we can. Okay, and we can also do this reversibly. So this is an oxidized functional group, so in order to do the reduction, we would need a reducing agent. 3 carbons, right? 3. Whoops, let's draw it on. I'm going to draw it on the top just to be consistent. 1, 2, 3. Okay. And you actually know this. I already taught you this. I taught you how to go from a ketone to an alkane, right? That was in chapter 15. H2 palladium. Usually on carbon. H2 palladium on carbon, or just H2 palladium, whatever. Reduces the ketone. Okay. Alright, so, and interestingly, to go the other way, this is a reducing reaction. going the other way, you use CrO3, chromium trioxide, which is an oxidizing agent. And you've actually seen this before, like to oxidize alcohols. We're using it for a different purpose. It does not have a simple mechanism, so don't worry about mechanism of this. But this allows us to go in the reducing direction and the oxidizing direction. Okay. I abbreviate these oxidizing and reducing conditions with bracket O bracket and bracket H bracket. No mechanism. Let's put a little note. No mechanism for either of these, so don't worry about mechanism for these steps. Okay. But now this is a ortho-para director. But this is remember our grouping? We had group 1, group 2, group 3. Is this group 1, 2, or 3? Simple alkyl. Is it group 1? No. Is it group 2? Nope. It's group 3. So this doesn't have all those problems with the overactivation. So if we just do a simple electrophile, it should probably go to the para position. Okay, cool. So we modulated the directing behavior. And if we take this and we want to turn it back into a ketone, how would we turn this back into a ketone? You would just use CrO3. Okay, cool. I'll say that, you know, this one you may also get ortho occasionally. For the most part, you can just assume it'll go para, but in the real world, yeah, you might get a little bit ortho electrophile incorporation, depending on the sterics of the alkyl group. So let's show this last thing in an example. I'm just going to be sloppy and write a circle. As long as we're not showing a mechanism of the benzene double bonds, using a circle is fine, whatever. So what if we need to do a synthesis of this, and I don't know, what kind of electrophile do we want to add? And let's not add it to the meta position, because this is a meta director. We want it at the para position, so maybe I'll do sulfonic acid. Okay, so can't do it in one step, because that is a, what kind of director? That's a meta. We need to turn it into temporarily turn it into ortho-para director. So maybe to do that, we'll kind of work our way from the beginning and the end backwards into the middle. Okay, so knowing our little strategy, the ketone, maybe we can reduce the ketone to a alkane with what? How do we reduce it? H2 palladium. Okay, now it's a nice ortho-para director. Great. How do we attach sulfonic acid group? SO3, H2SO4, chapter 15. Cool. Now it's really simple. This is easier than that last problem we did, because we don't have to worry about all that temporary deactivation and stuff. All we got to do is now turn the alkane back into a ketone. How do we do that? Alkane back to ketone. What was the oxidizing condition? It's CrO3. Okay. Cool. All right. And you know, having in this open note version of this course, you have access to all the reactions and conditions. You need to have really good notes, index cards and stuff, so you can look these up. When I teach the course in a sort of lecture environment where you have exams and have to memorize everything, sometimes I allow people to abbreviate things. Like I might say, okay, you can say oxidation for a miscellaneous oxidation, and even forget that it's CrO3, or like what is it, and I would, if it's a miscellaneous oxidizing reaction, these kind of abbreviations would be fine. In the OpenNote version, you have access to all this stuff, so you should be able to write all the reagents and just have really good notes, and you can find this stuff in your notes. Okay. Cool. Okay, so we're still on number 6, which are these synthetic strategies. But we're on C now, a third one. Alright, what's the third one? The first one was kind of protecting to temporarily deactivate. The second one was modulating the directing behavior, right? The third one is protecting, another kind of protecting, but rather than protecting the substituent, like to temporarily deactivate it, we're going to protect the aromatic ring itself, which sounds crazy. Protect the aromatic ring. I'm going to put a exclamation point and a question mark. Like, what does it mean to protect the aromatic ring? What we'll see is this allows us to generate ortho-disubstituted derivatives. Ortho-disubstituted. What does that mean? Ortho-disubstituted basically means two things that are ortho to each other. And by protecting, we have a cool protecting strategy for aromatic rings. That's not that crazy, but recall, this is, I guess, from chapter 15. Recall from chapter 15 that if you got a benzene and I want to attach a sulfonic acid group, remember that's something we know how to do, right? So one of the chapter 15 reactions. What you might not remember is it is actually reversible. When we initially told you about it, I explained you can put it on and you can also take it off. And this, because of that, this can serve as a protecting group strategy, right? How do we put it on? You know this. You know the forward direction. How do you do it? It was SO3H2SO4. It's actually a really easy reaction, really easy mechanism too, because that's a superelectrophile. It's like we're reacting this directly with a superelectrophile and it attaches, right? What you may not remember, so you know the top mechanism, it's just a EAS, right? EAS. To go the other way is H3O heat. Okay? And this is actually one of the homework problems, I think, in chapter 15, is like proposing a mechanism for this to go backwards. And I think that it is basically the exact opposite of, like if you go from here to there and draw the mechanism, this is the exact opposite. See, it's the key intermediates going backwards, right? And that's how you do the acid hydrolysis. You might want to practice that just for fun. We'll say reverse EAS. Reverse of the EAS mechanism, right? If you want me to go through it, you can also ask in office hours. I think we did it in one of the recent office hours, so you might be familiar with this. Okay, so we know how to put it on, we know how to take it off. I'm not going to show the mechanism here and how to take it off, but if you ask me in office hours, I'll do it. But what's cool about this is this allows a temporary blocking strategy. Of the para position, because the para position is the one that usually reacts. So we need to temporarily block the para position. This gives us an opportunity to do that. Okay, so I'm going to demonstrate it in a cool little example. What if I got benzene And I want to make bromochlorobenzene, ortho. Bromochlorobenzene, ortho. How am I going to do that? Okay. I think this is a case where going in the forward direction might be the easiest, I guess. I don't know. Sometimes retrosynthesis makes a lot of sense. Sometimes going in the forward direction works too. Okay, so which do we want to put on first? Bromine or chlorine? And what are those? Are those orthopara-directors or meta-directors? So they are orthopara-directors, right? They're orthopara-directors. Both of them are. So there's nothing different about their directing ability. So who do we want to put on first, and how do we do it? I don't know. Let's put the bromine on first. Br2, and then what? It's Br2 and FeBr3. So now the question is, how can we get that chlorine on there and have it ortho, right? Because if we just chlorinate now, where's the chlorine going to go? Well, this is a orthopara-director, so the chlorine would probably go to the para position, right? We want it ortho. Aha! So now this shows the beauty of C, which is we can just attach a sulfonic acid to the para position, right? And then we can install the chlorine, and then we can remove the SO3. Isn't that cool? All right, so how do we do it? How do we put on the sulfonic acid, and what does it look like? Of course, the that's an orthopara-director. So it's whatever we add is going to go para. And what's the reagent? It's up top. Of course, it's SO3H2SO4. All right. Now, when we install the chlorine, it helps that this is an orthopara-director, and this is also a meta-director. So they're saying the same thing. There's no competition effects or anything. This is saying I want it to be meta. This is saying I want it to be orthopara. So it's basically saying that, or there or there, which are the same. And so now we're ready for our chlorination, Cl2 FeCl3. Cool. And all we got to do now is wipe off that sulfonic acid with H3O heat. There we go. That's pretty cool. That's this strategy of temporarily blocking the para position in order to generate orthodisubstituted derivatives. Generate orthodisubstituted derivatives. Okay? Sweet. Okay. And all right. Okay, last little strategy. It's not that big of a deal. This one's a little easier than the other ones, but it just we're pointing out here that Friedel-Crafts reactions, FC reactions, which are the alkylation and acylation reactions, do not occur on strongly deactivated rings. Friedel-Crafts reactions do not occur on strongly deactivated rings. And all this really is going to mean is that sometimes when you're planning a strategy, you may need to consider two possible strategies, and one will work and one won't work. That's usually what this means. Okay, so example. What if we got benzene and we're like, I need to make ketone nitro. Okay, firstly, they're both meta directors, so if I put this on and that, and then this one, that'll, you know, this will direct that, or this would direct that. So it doesn't matter which I put on first, right? They're both meta directors. So, but there's two strategies, and one's going to work and one's not. So my two strategies are, which one won't work? Friedel-Crafts reactions do not occur on strongly deactivated rings. So if I have a strongly deactivated ring and I try to do a Friedel-Crafts, it's not going to work. So that just shows, well, here's our two strategies. One is going to go this way, one's going to go this way. In the top one, I'm going to envision attach the ketone first. In the bottom one, I'll envision attach the nitro first, and I'm just keeping the orientation the same as the product, okay? The way it's drawn up here. Alright, so what's the reaction to install a ketone? Well, it's acid chloride, AlCl3. That's the Friedel-Crafts acylation reaction, right? How do I nitrate a benzene? That's HNO3, H2SO4. Chapter 15, both of these, right? And then it's like, well, if I was doing the top strategy, the next step would be to nitrate the ketone, HNO3, H2SO4. And that would make that. Or in this strategy, it would be, let's do a Friedel-Crafts reaction. Nitro is a meta director, so cool. Alright, so which strategy works and which strategy does not work? They look like they're making the same thing, right? But our problem is that the Friedel-Crafts reactions do not occur with strongly deactivated rings. So if it's strongly deactivated, there's going to be a problem. And so that would suggest that if I have the nitro, which is strongly deactivating, and I try to do a Friedel-Crafts reaction, that is not going to work. Okay? That's all the rule says. So what's our best strategy? Probably first do the ketone, and then do the nitration. That's the whole issue in a nutshell. Okay? Cool. Okay, so we're done with the strategies. We've done a lot of cool stuff here. What we're going to try to do is tie these things together and all the neat chapter 16 and 15 things together to do some more synthesis examples. And this will get you ready for these kind of problems on the quizzes or whatever. So let's just try some problems and see how we might approach them. So these kind of combine all the different strategies, and you have to think a little bit more about which strategy to use. Let's take benzene and react with some stuff to make that. Okay? Okay, so what are we going to do first? Question mark, question mark. All right, what's going to be the overall strategy? And what you got to do is think, you have to look at the two substituents, and you're like, well, what's the relationship, and which strategy should I use? Well, and what kind of directing behavior are they? Well, a chlorine is a what director? Chlorine is an orthopara director, right? An alkyl is an orthopara director. That causes a problem, because this would not direct the installation of this, nor would this direct the installation of that. But we do know that alkyl can be sort of shuttled back between alkane and like the ketone version, right? And if it's the ketone would be a meta director. Assuming this was a ketone, it could install the chlorine meta to it, right? So which thing are we going to put on first? We're going to put on this, maybe as the ketone version, right? Or are we going to put on this first? it makes sense to put on the top and then use that, you know, change its oxidation state around so that it can install the meta thing. Alright, so how do we do it? And maybe we can, we'll try to go backwards. We'll see what how backwards works out. Okay, so, okay, what's the last step, maybe? Alright, so assuming this was actually a ketone, and the ketone would install the metachloro, maybe we should just draw the ketone version. Here. Right? And what's the magic conditions to remove a ketone from one of these guys? Remember, it's H2, and which metal was it? Was it nickel or palladium? So for ketones, it's palladium. For nitro, it's nickel. Maybe you can remember nitro-nickel, NN. Yeah, so it's palladium though. H2 palladium. Okay, you can look back in your notes for that. All right, so now it's cool because this thing is basically, the ketone is a meta director now. It can install the chlorine. So how about we just envision the ketone and no chlorine, and how do you put on a chlorine to a meta directed ketone substituted benzene? It's, what is it? Something and something. It's Cl2 FeCl3. Alright. Okay, now we're actually set because we can actually go, we don't have to do all the shuttling back and forth of a alkane to a ketone and back and forth. Because my point is we can go straight here. We can go straight to the ketone, right? That's just a, what kind of reaction is it? We're going to attach that with a what on it? What's the thing you have to attach? The functional group called that attaches ketones. It's the Friedel-Crafts acylation. So essentially that top thing with the chlorine on it, right? And what? What else do you need? Not just that. AlCl3. This is the Friedel-Crafts acylation. Acylation. Acyl means double bond O. Alright, that was fun. Now they get moderately more complicated. I think this is maybe a, I want to say homework one of the homework problems. Let's find it. Chlorine, O2N, bromine. Okay. Chlorine, nitrobromine. Alright, so I think it's 40F, chapter 16, question mark. I'm not totally sure. One of the problems has a whole bunch of synthesis examples, and you can definitely try them, and I'd recommend practicing these a bit. Okay, so this is a moderately challenging one. Alright, so what the question is, do we put on the nitrogen first, do we put the chlorine on, or the bromine on? Well, and what's the directing behavior? Well, nitro happens to be a meta director. These are not meta, right? Chlorine is an orthopara director, bromine is an orthopara director. But the thing about nitrogen is we have a lot of options. We can change its directing behavior. We can reduce it to NH2. And we can also kind of modulate its activation level, because NH2 is super active. We can turn it into an amide and make it a little less active. If you do that, it actually this is a really cool one to put on first. Put it on, and we can very carefully control the installation of the chlorine and the bromine. Okay, and of course, once say this is all set up to attach these. Which one would we put on first? Probably the para, because para goes easy, and then we go ortho for the other one. Okay, so that's my strategy. There may be other ways to do this, but I think the easiest thing to do is just attach the nitro and then we can worry about the chlorine and bromine. So I'm going to try going in the forward direction. Nitration. Yeah, because how do we install nitrogen? There's only one way to do it. You can't install NH2, for example. There's no way to just say, like, turn this into an NH2. All you know is nitration, right? So let's do HNO3, H2SO4, which will nitrate it, and we'll put the nitro on the bottom left. Okay. Alright, and now what? That's a meta-director. That's a problem, right? That's a meta-director. But we can turn this into an orthopara-director. How do you reduce a nitro? It's H2 and a metal, not palladium. It's actually nickel. In reality, H2 palladium, I think, will actually reduce nitro also. But the book kind of emphasizes nickel. And you can remember nitro, nickel, N, right? H2 nickel. And that reduces the NO2 to an H2. But now we got a problem. Even though this is ready for orthopara direction, you know, we have a problem that it's overly active. So now we have to do the temporary deactivation as an amide. And you just use, how do you attach this 2-carbon piece with acetyl bond O? It's acid chloride, pyridine. No mechanism yet on that. We'll learn the mechanism later. But that makes this. This is a super cool intermediate because we can carefully install one thing, carefully install the other thing. Okay. Alright, so now we're ready to maybe install what? The bromine. Because the bromine's para. The first thing we're going to install will always be para here, right? So we do Br2, FeBr3. I'm having trouble drawing. There we go. There's our amide. The amide's bent up, whatever. Make it a little nicer. Okay, cool. So the amide's kind of bent up. Anyway, now actually, this is it's an interesting point because we should be able to install the chlorine right now, right? This is going to bother me. I'm going to fix this. NH. There, that's a little better. Okay. This is kind of cool because it's still, we're modulating the activity, so it's a little less active than NH2. And it's an orthopara director, right? Orthopara director, but this is also an orthopara director. So which one's going to win when we put on the chlorine? This brings up a great point, right? Who's the greatest activator? Remember that? The greatest activator wins. Is this the greatest activator or is this the greatest activator? So go look at your greatest activator chart, which was, I think, earlier, last section of chapter 16, the greatest activators. This is the greatest activator. That's a lesser activator. So this decides where that chlorine is going to go, and it's going to be orthopara to it. Para is blocked, so it's going to put a chlorine. Ortho, right? Cl2, FeCl3. See what we did? We did an ortho-directed chlorination, and the nitrogen decides that it's going to be ortho to it. Okay, so it looks like we're really close, but there's two things that have to be done. First, we got to wipe off the protecting group. The second is we have to and that'll give us an NH2, right? It'll make NH2 basically. And then we have to turn the NH2 back into the nitro group, and that's an oxidation. NH2 back to nitro. Okay, so to do this, I'm gonna actually have to abbreviate because I'm out of space. Should have drawn this on a new page. Okay, and I'll use some abbreviations too. You should be able to draw the intermediate right here. First thing is deprotect, so it's acid, H3O plus, maybe a little bit of heat, and bracket DP bracket, deprotect. The second thing, that turns the NH2, sorry, it turns the amide into an NH2, it deprotects the acetamide. And then the second thing is once we have NH2, how do we go back to NO2? And that's the oxidation. You got to go back and look at your oxidation reaction, which is, it was the weird CF3OOH thing. Okay, and that's it. Cool multi-step synthesis from benzene to this sort of nitrochlorobromo thing. Alright, cool. I think this was one of the homework problems. You might check it. Try it yourself also to sort of review this. Okay, I think we have one more. I want to say we're on number 7, which is synthesis examples. I want to say it's 40G, but I don't know that. I think it is. Okay, so benzene to bromonitro. Benzene to bromonitro. Okay. All right. So being orthodisubstituted, which one? What's the rule? Remember the trick we're going to use. We learned that when you're making orthodisubstituted, probably you're going to do something, put something on, block the para position with a what? What's that thing we block it with? So you put on something like the bromine, block the para position, and then install the ortho thing, and then deblock the para position, right? There was that sulfonic acid thing is maybe the third trick we learned. Okay. The other question is, which thing do we want to install first? A bromine is a what kind of director? A bromine is a orthopara director, right? Nitro is a meta director. So if we install nitro, we're actually going to have problems, I think, because even though we can convert this to an orthopara director, so it's a bunch of steps, it's extra work. So my suggestion is, since this is an orthopara director, let's put on the bromine, block the para position, and then it's still an orthopara director, and this is a meta director then once it's blocked. And then with that, we can install the nitro, and we're done. That's a pretty easy problem if you do it the right way. So I think put on the bromine first, Br2, FeBr3. If you do this the right way, it's a pretty short synthesis. If you do it the wrong way, it turns into like a 20-step synthesis. So you can try the long way also just for fun, for comparison. But the long way will be install the nitro first, and then it's going to be you're going to have to bend over backwards to get on the bromine at the right place. Okay, but with the bromine on, now how do we block the para position? Like a sulfonic acid. How do we do that? It was SO3 H2SO4. Okay. Now we're set because this is an orthopara director, this is a meta director. They're both saying to install the nitro right there. So HNO3 H2SO4, right? That's how you install a nitro group. Nitric acid, sulfuric acid. keep the sulfonic acid on. See ya. NO2. Alright, so we're good there, yeah. And now all we got to do is what? Take off the sulfonic acid. And how do you do that? That's a deprotection, and in this deprotection reaction it's H3O heat. So that is how you do it, how you finish it all off, right? That's pretty easy. For fun, if you want to try the alternate strategy and practice, just for practice, I would never, I mean, if I was doing this in the real world, I would do it as easy as possible. But for practicing your reactions, it almost makes sense to do it the wrong way. A wrong way that'll work, but it takes 1,000 steps. So the wrong way would be nitrate first, HNO3. Okay? And now you're going to have to do a whole bunch of steps. It might be good practice for you, but of course it's the bad way to do it, but you could practice all the steps. Because now if you nitrate it, then you have to convert this to an orthopara, it's meta initially, right? Convert it to orthopara director, so and then it's NH2. Turn that into a deactivated orthopara director, so with the amide. Install a sulfonic acid on the end, you have to do that still. Then you could install the bromine, and then you have to remove that protection, the amide. Then you have to reoxidize it. So it's not 1,000 steps, but it's almost 1,000 steps, right? So you can do this one too. It's the bad way, you know, bad but educational maybe. And then you should be good. All right. I think we're done with this chapter. I think we're done with this chapter, yeah. Alright, we're going to just jump into chapter 17. We have a few minutes and do a couple of the easier things, and I'll get them done with next time. And like a lot of the chapters, we break up the conceptual points from the kind of reactions and mechanisms and stuff. Alright, so chapter 17 is like this. Alright, so how do we name aldehydes and ketones? You know, if you think about the parent chain, like hexane, it could turn into either hexanal or hexanone. So it's usually something like Al or ONE at the end. So this molecule is pretty simple. What's the naming of it? 1, 2, 3, 4 is butane, butanal. What about a ketone, like 4 carbons, ketone on number 2? What do you think? It's going to be butanone, but you should define the position. It's 2-butanone. What about cyclohexanone, which is a 6-member ring with a ketone? The numbering would begin where the ketone is, so it goes 1, 2, 3. So it's 2,3-dibromo cyclohexanone. What about this? Probably find the longest chain where the ketone is 1, 2, 3, 4, 5. So it's something 2-pentanone, and where's the methyls? On carbon 1, 2, 3. It's 3,3-dimethyl, 2-pentanone. So always build a name from right to left, essentially. 3,3-dimethyl, 2-pentanone. Aldehydes on a benzene are usually called benzaldehyde. So this thing by itself, without the bromine, is called benzaldehyde. And the bromine is on carbon 2, because you would number around the ring from the aldehyde. So it's 2-bromobenzaldehyde. Or you could call it ortho-bromobenzaldehyde. That's a common name also. What about this one? So you have a bromine and a nitro. You put even though the nitro is on 2 and the bromine's on 4, you list the bromine first because it's listed alphabetically. So it's going to be 4-bromo, 2-nitro-benzaldehyde. 4-bromo, 2-nitro-benzaldehyde. How do you name it if it's like a substituent, like an aldehyde on a ring or something like that? How would you do that? You would call this cyclopentane pentane, which is cyclopentane, and then the aldehyde you call carbaldehyde. So it's it's kind of a weird naming, and a lot of naming's weird, but that's how you would go about naming that. Cyclopentane carbaldehyde. Carbaldehyde refers to the aldehyde substituent in this case. Okay, and if you have that, what's this? It's something cyclohexane carbaldehyde. Something cyclohexane carbaldehyde, and maybe 3,4-difluoro, right? Fluorine, 3,4-difluoro cyclohexane carbaldehyde. All right. What about this? And so the aldehyde or ketone will define the numbering system. An aldehyde is really easy because it just becomes number 1. It's like 1, 2, 3, 4, right? 1, 2, 3, 4. So it's maybe 1, 2. It's something butanal, right? Butanal. Something butanal. And it's 3-bromo-4-fluorobutanol. 3-bromo-4-fluorobutanol. This one's pretty easy, right? 1, 2, 3, 4, 5, 6, 7. So it's heptanal with the methyls on 1, 2, 3, 4, 5, 6. 4,6 dimethyl heptanal. All right, I'm showing chirality, and you don't have to worry about RNS for this course. And whether or not I even give you nomenclature problems, I haven't decided yet, so you may or may not see these kind of problems. But do we number on the right side, from the right side or left side? Right side or left side? Probably the right side because it's closer to the ketone, right? So it goes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's maybe 3-hexanone is the main chain. 3-hexanone, and you have a bromine on 2 and a chlorine on 4, right? 1, 2, 3, 4. 2-bromo-4-chloro. 3-hexanone. 2-bromo-4-chloro, 3-hexanone. If you were designating the stereochemistry, you could do that. We're not going to have you do that in this course. Okay, a cyclic ketone. A cyclic ketone would be, this would be some kind of, and we number in the end in the direction of the closest substituent. This is a pretty crazy name, but we're just practicing. This is ethynyl. It begins with E. This is bromine, so this B. So it's going to be 5-bromo, 3-ethynyl, 5-bromo, 3-ethynyl, cyclo what? Cycloheptanone, right? 7 carbons with a ketone. 5-bromo, 3-ethynyl, cycloheptanone. Let's try this one going backwards. It's always easier going backwards, right? 7-hydroxy, 7-methyl, 4-octene, 2-one. Okay, so with this kind of name, drawing the structure should be pretty easy. You think like 8-carbon chain. Ketone is on number 2. Ketone's on number 2. Alkene maybe on number 4. And then we have a hydroxy on 7 and a methyl on 7. There we go. Ketone on 2. Alkene on 4. 1, 2, 3, 4. And then methyl and hydroxy on 7. Okay, I think we'll just finish this last little bit and we're done. All right, so very easy ones that you should just know. What's this? 1-carbonaldehyde. You know this one, right? Formaldehyde. And this is not an aldehyde or ketone, but it's form something acid, right? Formic acid. Formaldehyde and formic acid. What about a 2-carbon aldehyde? It's like acetic acid, like acetic acid, but this is what kind of aldehyde? Acetaldehyde. Okay. These are just other ones you'll see from time to time, some ketones. This one's called acetophenone. This is called benzophenone. Memorizing these is not necessary. It's kind of silly. And that's it. We'll continue next time.